Welcome to I Can Science That. The other day we hosted a discussion where Flat Earth friend of the channel Godric came on, and among other things we discussed the Eratosthenes experiment. We agreed that we should get some flat earthers and some globe earthers together to reproduce the experiment, or an homage, if you will, to that experiment, to see for ourselves not what happened thousands of years ago or what it says in the textbook, but something that cannot be faked, what we can test for ourselves in our own neighborhoods. So this is the Flat Earth test, and this is how you can participate with us. In honor of the summer solstice, we chose June 20th. June 20th is coming up soon, so get ready for this. Fortunately, this is a very easy experiment to do, easy to participate, and so everybody can join in. It doesn't take much effort. It's Father's Day also, so it's a good chance to get out with the kids and force them into some family science activities. In the simplest possible terms, this is what we're going to try to do. The flat Earth hypothesis suggests that the surface of the Earth is essentially flat and the sun is somewhere up above that it is always above that, and it should be in that same location to any observer anywhere that can see the sun. So what we'll do is at noon, we'll measure the angle to the sun from an observer here, and then simultaneously we'll measure the angle to the sun from a distant observer, a different observer in a different city. So we'll all be able to participate from different cities. Wherever you are, you go out and you measure your angle, and we'll take a pair of these, any pair of these, and if we know the distance between those two cities, we can then, using those angles, figure out exactly where the sun is. And from that, we will be able to measure the height of the sun circling above the flat Earth. Okay, but you know I'm not going to let you go with it that easily. What if the Earth is not flat, right? We have to consider that possibility. The Earth might not be flat. And so to confirm it, we'll need at least a third location. So the hypothesis suggests that from any location, we should all be looking at the sun. And so we'll get at least 3, hopefully much more than 3 different locations, and we'll confirm that they all give us this same height of the sun above that flat plane. Now, we won't be able to do this simultaneously. Instead, what we'll do is everyone will do it at their own local noon. And that will tell us, since the hypothesis says that the sun stays at that same height above the plane, then at noon we'll do this, and then we'll be able to use that to see what the height is at noon. But wait, what about the globers out there? I know that this channel is dominated by mostly globe Earth believers, and maybe we have a few flat Earth followers. Hopefully all you flat Earth followers will join us in this experiment. You can do it from anywhere in the world. But we have an experiment for the globe earthers as well, so they don't feel left out. In fact, it's the exact same experiment. What I want you to do is go out wherever you are and measure the angle to the sun at that same time, at your local noon on June 20th. And what the hypothesis says is that the sun is so far away that no matter where you are on the planet, the angle to the sun in this diagram is going to be approximately parallel. So we'll collect many observations from many different people and plot the angles onto a diagram like this at the location you were when you took the measurement with the angle that you took, and see if we get these parallel lines that the hypothesis suggests. All right? If it does, if this confirms our hypothesis, we can now use these measurements to calculate the radius of the Earth, much like Eratosthenes was said to have done. How does that work? we need these angles, and we also now need the distances between cities. Based on the angles, we can then assess what is the angular distance between the two cities. And if we now know the distance over land between the cities, which we'll get from Google Maps as we do. If you're skeptical, confirm it by driving between the two cities and looking at your odometer. If we have the distance over land and this angle here, we can now predict the circumference of the Earth, and from that we can get the radius of the Earth. How can you participate? We need lots and lots of observations, and I want to see some flat earthers out there joining in this effort, right? Let's get out there and make this a joint effort between all sides. We have Godric, who is a flat earther, who came on the channel and asked us to do this experiment. We have many globe earthers who are willing to participate. We need to get many observations to make this really solid. So how do you do it? We agreed in honor of the solstice. It doesn't need to be a solstice to do this. You can do this any day of the year, but the solstice is coming up on June 20th. What are we going to do? To make things very easy, I want everyone to do it at their own local noon. You can use suncalc.org to find out what local noon should be for you in your area. Go out at noon, get a stick that points up straight up from some flat ground. Let's find a nice flat patch of ground. We don't want grass. We don't want a hill. Nice level surface and some kind of stick. It doesn't matter what it is as long as you can measure it and you can measure its shadow. And we need to make sure it points up straight up. We don't want it leaning at an angle. We want it straight up and down. So you measure the shadow of the stick. You measure the stick. I'll need those measurements. How long was the stick and how long at noon was the shadow of the stick? At your local noon on June 20th. Now, local noon does not mean 12 o'clock. That means when the sun is at its highest point, right? Because of the vagaries of time zones and daylight savings times and other things that involve geometry of the sun and the earth. The local noon is different for everybody. So what you want to do is use suncalc.org or timeanddate.com to find out what your local noon is, and I'll show you that here in just a second. And then send me your results. I will have a Google form. Look for it down in the description, and I'll also pin a comment where you can find your copy of the Google form to anonymously submit your results. I won't track anybody's information with this form at all. This is just a way to anonymously collect the data. There will be a slot on the form for you to put your name or how you want to be addressed, if you want to be addressed. That's optional. If you want me to give you a shout out on this later for having contributed, that's where you put that in there, and I will do that. If you don't want to be called out, you just want to be anonymous, then don't put anything and I won't know where the data came from. All right, so that's the experiment that we're going to do. Let's go now into the explanation. And this is where I would normally give the trigger warning that we're going to get into some math here, and I know some of you don't really enjoy math, but for this one, let's not do any math at all. No math. We're going to do this with nothing but rulers and protractors. The idea is this. Here we are on a nice level surface, and we've got our stick, our stick sticking up straight up from the ground. The sun is somewhere. It's going to be south of me, for example, somewhere south of me. The light from the sun comes down and it will hit the top of the stick right there, hits the bottom of the stick right there. In between here, the sun is shining here, the sun is shining here, but right here the stick is blocking the light of the sun and it will cast a shadow on the ground right there. So what we're going to do is we're going to use a measuring use a yardstick, use a measuring tape. You're going to measure the length of the shadow. You will also measure the height of the stick. You write those two numbers down. There'll be a spot on the form for that. And that's all you really have to do. I will do all the rest for you. If you want to follow along, this is how you can do it completely with no math. We will want this angle right here. We could use trigonometry to get that angle, but we don't need to. Instead, all we got to do is draw this whole thing to scale on a piece of paper. Whatever scale you choose, as long as you choose the same scale for horizontal and vertical. So it could be a 2-to-1 scale, a 1-to-2 scale, a 10% scale. Whatever scale fits on your piece of paper, you get a ruler and you measure out a line that is exactly the correct scaled length of the shadow. And also a line that is the correct scaled length for your stick. Just do that. Connect those two with a nice straight line. Use your ruler as a straight edge and connect those two, and then break out a protractor and we will measure the angle that you measured. This is the angle that the sun makes at your location at that time on that day. So here we have, like for example, we measured about 39 degrees there showing on the protractor. So now we have the angle to the sun, and that will work into that diagram that I showed earlier where we needed the angles in order to predict the spot where the sun is at. Let's show how that works. Again, no trigonometry, just going to do this with straight up measurements. You are here, make a tick mark on your paper and a nice straight level line here for the surface of the earth. This is you. And we have another city. You'll take a second observation from someone else. Like, let's say this is someone in Seattle and this is someone in Los Angeles. What is the distance between them? North-south only, right? We want to do the north-south direct distance because everyone's doing it at noon. And we will use our ruler to set a scale for how far apart those are. All right. And now we'll break out the protractor and take whatever angle the Seattle person measured, and we'll shoot a line at that angle. We're saying, for example, we're saying here that was 45 degrees. So at 45 degrees, boom, we'll shoot a line, nice straight line along that angle. And we'll move on over to the other city, and whatever angle they measured, we'll shoot a line there too. We got 70 degrees for them, apparently. And so we'll, boom, we'll shoot that angle right on up there. And then what does that give us? It gives us this intersection right here. This point where the two observations cross, that's the actual location of the sun circling above the flat earth. And we can now find out how high that sun actually is. How do we find out? Well, we just take our ruler. We can now scale, get the scaled height above the flat earth for how high up is that sun. All right, but I mentioned before, we're going to do it with at least 3 cities. Make sure you use that same scale that we established. We drop in the 3rd city, we use the protractor and measure their angle, and dang, this is what we're looking for. All observers should see that same sun. They're all looking at the same sun. They should all be looking at the same point in the sky, and that will tell us how high that is. All right, but what if it doesn't work? What if the lines don't meet up? If the lines don't meet up, then where is the sun? Where's the sun? It doesn't work if the lines don't meet up. So if there's like, a little bit of error, that's just going to be normal from measurement and diagram-based error. But if it's dramatically wrong, like I'm drawing here, then what that would indicate is that there was something wrong with our original premise. The original premise that we built this whole experiment on was that the Earth was flat and that we all would see the same sun at the same spot. So if we get this result, then it tells us one of those premises was incorrect. So we'll be looking out for that. But what about our globe friend? We're going to say we take the latitude of each city that the observations came from, and we'll place that onto just a circle. Just draw a circle on a piece of paper and use your protractor to find your latitude, the latitude of your observation. And that'll be your location on this hypothesized spherical Earth. Using your protractor again, you will find the angle of the observation that you took. And you say, okay, the sun was at, looks like it was about 43 degrees up from the horizontal here. And so that must be where the sun is, somewhere along that line. And we'll repeat this process for the other cities. For example, here's another city and their observation, and here's another city and their observation. What we're looking for in the hypothesis is that these lines are parallel. If the lines do come out parallel like this, that confirms the hypothesis, and we can use that to establish the radius of the Earth, not as an assumption, not as a presumption, but as a literal measurement. And how will that work? Well, we're going to need the distance along the surface between those cities, and that will tell us the radius. But watch out for this scenario. What if they're not parallel? What if we do all of this effort and we come out with measurements that are all over the place and they certainly do not line up according to the hypothesis? Well, that would mean one of the premises of the hypothesis was incorrect. We hypothesized that the Earth was roughly spherical and that we were all looking at a very distant sun. And that light travels in straight lines between that very distant sun and ourselves. So if we get a result like this, that's going to tell us one of those premises was incorrect, and we'll need to go back to the drawing board. Local noon, what is that? How do I get it? What is SunCalc? Let me show you real quick. suncalc.org. All right, suncalc.org. This is very easy to use. We'll just close that. Let's say you're in Madrid. Apparently I'm in Madrid here. I want to know on June 20th, what is local noon? And I can use this. All I do is I come over here to the date right there. I'm going to choose June 20th. And right here, culmination. Culmination means the moment when, in the course of the day, the sun reaches its highest point. So we want the sun at its highest point above you when you take this measurement. And if you just click on the time, clickety-click, it will take you to that in the diagram. So all you got to do is look at this, and it's in 24-hour time here, so that means 14:15:42, so 2:15. So at 2:15 in the afternoon in Madrid, that's when you'll want to do this. Let me put it up there in the linkity link. Flat Earth Peer Review is trying to organize a similar type of experiment. He wants people along this line of the prime meridian. The prime meridian is this line right here that goes through England and goes through Spain and it goes through parts of Africa. So if you can get to one of these locations, if you happen to live near that point and you want to participate in his experiment, I'll put the link up there and go check that out. But if you can't, you want to participate in something, let's do this. Let me show you, for example, my location. I'm going to come over here. I don't want to be in Madrid. I'm in Los Angeles, California. And here I am, Los Angeles, California. That'll work. That's close enough for where I'm at. And it shows my culmination, and my spot is going to be a little before 1 p.m. If you need any help finding this, contact me. I'll be happy to tell you. You give me your latitude and longitude or the name of the city that you're in, and I will punch in this for you and tell you what time to do that. Let's take a look at that form. Down in the description, there will be a link for a Google form where you can fill this out. Again, if you don't want to use Google Forms, here's the link. If you don't want to use Google Forms, you can instead just email me the data and I'll enter it by hand myself. So here's what the form looks like. The first question, just which group are you? I'm hoping we get representation from the flat folks and the round folks. Fill it out if you want. I've marked that as optional. Don't have to. Definitely optional if you want to put your name. So like, do you want to put your name? Yeah, you can put like, I can science that. Put your name, put your email, put your YouTube, whatever you want. If you want to put anything at all, you can just put that. And then you might want to say, hey, like, you know, don't contact me, but hey, give me a shout out with that name, and then I'll do that for you. Or you know, you say no, I don't want that. Okay, those are all the optional questions. Now we're into the required stuff. Please do tell me the latitude and longitude of your location, and if you don't know that, that's fine too. Just tell me where you're at. So like, you know, I'm in Madrid, Spain. You know, I'm not in Madrid, Spain. It's Los Angeles, California. Yeah, I'm gonna say, better put that just in case I don't recognize your city. Okay, so that, and I'll look it up for you, or put your latitude and longitude in there. Make sure you put north, south. If you're just gonna give me a number, I won't know what you mean, but if you give me your latitude in north or latitude in south, that's really the important number. I'll throw the longitude in there as well so I can confirm the time. And the date. Everybody should be putting in June 20th, but if you do it a day late, do it a day early, that's all right too. We'll accept it. Okay, and then what time? So like we found, I think, that it was supposed to be 12:54 p.m. So, you know, maybe I'm a few minutes late, so I'm gonna go 1:05 p.m. or something, right? Fill that in. How tall was my stick? Put in your measurements. I don't know, 43 centimeters. Give me the units. Make sure you give me the units. If you don't, then I don't know what I can assume, whether that was 43 inches, 43 centimeters, 43 meters. I don't know, right? And how long was it? I don't know. It was 22.4 centimeters. I don't know. So you know, when you do the experiment, fill this in. Don't make them up. Fill this in. And then last, there's an optional. If you did take these numbers as I outlined and turn that into an angle, go ahead and give me the angle. If you want, and if you don't have to. If you don't do it, I'll do it for you. Okay, so yeah, just hit this and hit submit. You should be able to see all the responses and edit your own response. I'm going to be editing my own response. In fact, I'm going to grab this link because I'm going to want to edit my own response when I actually do this experiment and change those numbers that I made up. Okay? All right. What's the point of all this? Well, if you think the Earth is flat, the point of this exercise is to find out how high the sun is above the flat Earth. You've often heard various numbers thrown around, and you've heard that it's very vague and it's not very concrete. This is us finding with an exact measurement the concrete height of the sun above the Earth, but maybe you're convinced that the Earth is a globe. This is us measuring the radius of the Earth. How many times have you heard from the flat Earth folks that you're just assuming the radius of the Earth? You can't measure it. This is our way of measuring the radius of the Earth. But actually, there's a deeper, more important reason to do this experiment, and to do it in cooperation with flat earthers and globe earthers. The reason for that is I have often heard flat earthers say that this experiment is inconclusive because it might show that this distance, we could calculate a radius based on this. But this diagram presumes that the Earth is a sphere, and it presumes that the sun is very far away. What if we didn't presume that? What if we imagined that the Earth was flat? As we just saw in the previous slide, we can get angles for that as well, and this experiment proves nothing. But without going into the math, let me assure you that the angles that we get from these two scenarios are different. They are not the same. We will get angles. Whether the Earth is flat or whether the Earth is round, we will get a set of angles. But the thing about it is they will be different. If the Earth is flat, we'll get one set of angles. If the Earth is round, we'll get a different set of angles. And the way we'll see that is these lines will cross. They will not be parallel if the Earth is flat. If the Earth is flat and we draw this diagram, we will not get parallel lines. If, on the other hand, the Earth is round and we draw that previous diagram, we will not find that all the lines line up and cross at that one point. Okay, so that is why we're doing it. We are testing the hypothesis. We have a pair of hypotheses here. Hypothesis A, the Earth is flat and the sun is close. Hypothesis B, the Earth is round and the sun is far. These are our two competing hypotheses, and this test will eliminate one of them. I guarantee one at least one of these hypotheses will be invalidated by this test. So let's do it, and let's find out for real using repeatable observations that we take ourselves, measurements that we do and nobody can lie about because we did them. Let's find out what's real. See you down there. Let's see you on June 20th with some solstice observations.